Can you see my screen?
Yes.
Wonderful. Okay, so hello everyone, and I'd like to kind of give a little summary of the recent, well, it's now 2 years ago, the recent paper on iron and oxygen isotopes in Kiruna-type ores. And as Adam said, it's a little bit of a review aspect in the paper, but it also has a good number of new data. But the goal of it was to bring this together. Various people have worked on iron and oxygen correlations. There was my master student, Franz Weiss, but also people from Adam's group have worked on this. And it was a good time to kind of put all the data my team has collected together and really kind of come up with a more comprehensive summary of this. And this is what I attempted to do there. And as Adam said, he was one of the reviewers for the story, but there were several other reviewers, and I mean, overall, reviews were good for it, but still, it was quite a job to get it all ready and published. So, but I'm very happy with it. It seems to get good citations, so hopefully people will use this rationale in the paper now in the future and exploit the correlations between oxygen and iron isotopes to unravel some of the processes in these type of ores. So I'd like to quickly start with a very brief summary. Well, at the moment, there is a lot of noise about rare earth elements, and this is, of course, important for various technologies. But iron is still the #1 metal that we are mining, and this will not go away. So this is something that will remain with us for quite some time. And certainly in Europe, the Kiruna-type apatite-bearing iron oxide ores are the most dominant source and have been for many, many decades. And as it happens, Sweden has the highest concentration of these deposits, with Kiruna being the prime situation for locating these type of ores. And therefore, Sweden is the top producer of iron ore in Europe. So these apatite-bearing iron oxide ores, they are often referred to, therefore, as Kiruna-type ores. And they are massive magnetite, but often associated with apatite. There is, of course, a lot of complications around them, but this is the simple mineral kind of components that we find in the most massive parts. They are often also grouped together with IOCG deposits, iron oxide, copper, gold, but there's big debate, and I have some colleagues, including some of the co-authors on my paper, that are not very happy with that. Others are much more favorable towards a link between IOCG or, well, porphyry copper type systems and the Kiruna type systems, but this is something that I guess we can discuss a little later as well. Now, usually these Kiruna-type ores, they happen to be associated with subduction system in the widest sense, and that's very interesting. And certainly in Sweden, they form lens-shaped or disc-like ore bodies, partly because of deformation. And we see that, of course, in younger deposits like Elaco, where they're kind of occurring in more circular outcrop patterns. Now, we have the very old ones here in Kiruna and Grängesberg and Malmberget. And then we have some younger ones in Iran, for example, and some very young ones, quaternary ones like Elaco. So there's good evidence that these type of deposits are or have formed over, well, quite some geological time, and they still likely are forming at the present day. I have some xenolith samples from Indonesia, from some of the volcanoes there. And I think there's actually some Kiruna-type ores forming right now on the Indonesian volcanoes as well. So I believe it's an ongoing process. It's a renewable process, therefore. So there is something like 350, probably a few more by now, prospects worldwide and deposits that would be labeled as Kiruna-type. And they often contain low titanium magnetite as the main ore mineral, and very fluor-rich apatite. Hematite is present, of course, and I personally like to think that there is the option of magmatic hematite, but often hematite can also be an alteration product or a hydrothermal overprint product. So the Kiruna-type ores, they're known for their large sizes and very high grades, and Kiruna itself has a pre-mining kind of reserve of 2 billion tons, I believe. Ulf can probably correct me later if this is not correct, but the grade can be very high, about 60%. So this is economically very attractive. So then the origin of these deposits is not fully understood, and there's a big discussion for about, well, 100 years or so. And there's two broad schools of thought. There's the magmatic school, and there is what I would term the hydrothermal school. And the magmatic one believes that it's essentially a magmatic type processes, either being directly formed from magma or magmatic fluids, while the hydrothermal school is more in favor of lower temperature processes, maybe about 500 degrees or below. And there would be processes like replacement and precipitation from these lower temperature fluids. Now, what I wanted to do in this study was to investigate the origin of these iron ores. And here I wanted to use iron and oxygen as the main elements that make up magnetite. So the hypothesis behind it is that magnetite that formed from magma should obviously be in equilibrium with the magmatic source. So there should be an equilibrium for the isotope values. And fractionation temperatures should obviously fall into the magmatic range. In contrast, magnetite that formed from low temperature hydrothermal processes should not be in equilibrium with magma or magmatic fluids, but if possible, it should be demonstrable that it's in equilibrium with low temperature hydrothermal sources. So in simple words, ore that formed from a similar source under similar conditions should show a similar isotopic signature. And for that, we have decided to look at a wider array of ore deposits and a larger array of reference samples. This was, I guess, the big clue about this particular study. So what we've done is we looked at Swedish ores, but we also looked at some iron ores from Chile and from Iran. And then we took reference samples, classic magmatic ones from layered intrusions, and also many active volcanoes. And in addition, we looked at some well-established low temperature or hydrothermal ore deposits, mainly from Sweden because they're well characterized here. And then we should, we believe, see these systematic differences. So when it comes to the approach, we had 14 samples from Kiruna, dominantly massive ore, 13 samples from Grängesberg, which is a little bit further south. It's less well known, but it's a good, well-behaved Kiruna-type ore deposit in central Sweden. And we also took some vein and disseminated samples from there. We had a small number of Elaco samples and a small number of BAFC samples from Iran. And then we had 6 well-selected additional hydrothermal ore samples, which included scar and SEDEX and BIF types. And we had 6 samples from layered igneous intrusions. And in addition, I took 13 samples of volcanic reference materials from all sorts of reference volcanoes, like Taupo in New Zealand, from Tenerife, Krakatau, and a few places like that, and Iceland, in fact. And we looked at those, and we're hoping to see a systematic pattern. So the hydrothermal ores, just to run through them very briefly, there is the Dannemora ore in Sweden. Then we have the banded iron formation at Striberg. And then we had some Banduria samples actually from Chile. And then we had some Björnberget samples, which is close to Grängesberg. But that's a kind of limestone interaction suite. So it's a little different, and it would be lower temperature. Now, when it comes to layered igneous intrusions, we went to the mother of all layered intrusions. We got some Bushveld samples, but also Panchihua in China, and then some Swedish samples from various places, and also most famously from Ulvern, where Ulvor Spinell comes from, and Taberge and a few others. And we then analyzed all of those. The Magmatic suite, as I mentioned, had samples from Tenerife, and then from Ruapeo in New Zealand. We had some Krakatau samples, and we had samples from the Troodos ophiolite in Cyprus, and also from gabbro on Iceland. The work started off with this gentleman here, Franz Weiss. He was a master student of mine. He is now an officer in the German army. He is in the Geo Corps of the German army, and he's building airports and things like that. And he's still kind of doing hobby geology, so I'm in frequent contact with him, but he can't join us today, unfortunately. But he did his master here, and he was starting to separate the minerals from these samples. And the study contains a total of 53 new oxygen isotopes that were done in Cape Town University. And we offer 58 new iron isotope analysis. At the time the paper was published, this was the largest compilation of new iron isotopes that was in the literature. Maybe there's a better one now, but 2 years ago, that was kind of larger than most other studies that have been out there. Now, a very quick background, geological background. There is Ulf in the top right, who is present today. And he has kindly allowed me to sample in the mine and also kind of in the surroundings. And the Kiruna deposit is, of course, in northern Sweden in Lapland. And it's hosted in a trachyandesite rhyolite series. And the rhyodacite or rhyolites, they are often ignimbrites and tuffs. The age is between 1.9 and 1.8 gigayears, and it's been regionally metamorphosed, and there's also some orogenic overprint here. But the test was partly about whether the iron and oxygen isotopes in magnetite would be stable or not, and I believe they are. So the host rocks are strongly deformed, as I said, and at the moment the mine is so expansive that the town actually has to be moved, which is a big topic here in Sweden for sure. And the mine is also going very deep. It's the deepest point in Sweden, in fact, with about 1,200 meters below. And the ore grade is very, very high. So there's vast amounts of ore being produced on a daily basis. The Grängesberg ore deposit, it's in central Sweden. It's about 3 hours drive from Uppsala. And it was mined until the mid-1980s, but then for various reasons, mainly political, to my understanding, it was closed down. But there's still efforts to reopen the mine at the present. And the age is a bit similar to Kiruna, and it's also hosted in volcanic country rocks, tasites, andesites, rhyolites. And there is also some metamorphic overprint. It's lower amphibolite metamorphism. And the area has been interpreted as analogous to something like the Taupo volcanic zone in New Zealand today. There is discussion about that, but I still think there's a kernel of truth certainly in that analogy. So it's certainly a volcanic subduction related setting. And the iron ore is dominated by magnetite. There's, of course, some hematite there as well. The ore grade is from about 40 to 60-ish, and there has been something like 150,000 million tons already mined, and there is maybe another 150 left. The ore deposit is lens-shaped, and in that little diagram on the right-hand side, the dark black material, that's the ore deposit, and there's various shafts going down. They are all flooded today, so if the mine is going to be reopened, it has to be kind of pumped out, which is a big job, but certainly there's ore down there. So you probably know this better, certainly Adam, you know this better than me. I've only been to Alaco once, but Alaco is a very young volcano, comparatively young volcano in northern Chile. And it's got this circular arrangement of magnetite ore deposits. It's about 2.1 million years old, and the rocks are hydrothermally altered, but there has been no orogeny or so going over this. And there is something on the order of 500 million tons of high-grade iron ore, and the grade is about 60% iron to my understanding. So magnetite is the main ore mineral there. Currently, it is not being mined. And when I was there 2 or 3 years ago, we were allowed in, but there was no mining activity. And the reason we were given is that it's too expensive because the altitude is too high. Most of the ore deposit is above 4,500 meters. And it's a classic place for petrology, nevertheless, because there's these amazing textures that look like lava textures. So there is lobes and bubbles and features that are distinctly lava-like. And this has, however, led to quite some discussion. Some people believe it is magnetite lava flows. Others are arguing that there has been whole-scale overprint, hydrothermal overprint of former lava with iron-rich hydrous fluids, and they could have led to the looks that we are seeing today. Now, I've never been to this place, unfortunately, Bafq in Iran, but I have collaborators in the geological survey there, and they supplied the samples. And here we have a large volcanic belt in central Iran, and there the Bafq ores are quite famous, and they're hosted in a mixed series of rocks. There is sedimentary rocks, dolomitic rocks, but also volcanic rocks, rhyolite rocks, and they are of early Cambrian age. And Stefan Peters, who is here today, he had a recent paper on these, and there was good evidence that the magmas had interacted with some of the sedimentary sequences there. So this would be quite sensible, I think. And there's something like 34 recorded iron ore mineralizations with something on the order of 1,500 million tons of ore at an average grade of 55. Several are actively mined, and I'm listing a few here. There's a field picture of an iron oxide and apatite intrusion into some rhyolitic country rock, and there's also some metasomatism going on. It looks quite like a dike as far as I'm concerned, but of course you might find other people arguing differently. So the geological setting is Neoproterozoic and early Cambrian, and it's also an active continental margin, therefore subduction type environment. So having discussed all this, I'd like to kind of plunge right into the data. So here, the plot that I'm offering here on the right is a delta 18O plot, and the orange box is what is traditionally accepted as the magmatic range, going back to the pioneering work of Mr. Taylor in the mid to late 60s. And it is intriguing, but all the suites we looked at, the colorful data are our own data, while the white symbols are literature data. We find that virtually all of the apatite iron ores, they start out in the magmatic field. Many of them progress into the left of the diagram, meaning that there was lower temperature phenomena playing a role as well. But the volcanic reference materials are almost exclusively in the magmatic field, of course. The layered igneous intrusions are as well. And apart from one sample for the low temperature suite, one anomalous sample, all of them plot left of the magmatic box. So there is quite some good evidence that the system works. And for Kiruna, Grängesberg, Elaco, and Bafq, and some literature work, mainly from actually Adam Simon's group from the Chilean Iron Belt, there is good evidence that the magmatic box is where everything begins. Of course, volcanoes cool down, so that the shift happens towards the left of the diagram is not surprising in my view, but the origin has to be, according to these data at least, has to be magmatic for many of those suites. Now, here's a close-up of the whole thing, and you can look in a little bit more detail. So there is yet more literature data. And as I said, if we take this one single anomalous guy in the bottom, the green chap out, then all of the low temperature hydrothermal magnetites are also actually outside the magmatic box. So what's going on with this anomalous chap? I don't know. We looked at it very carefully, and it was associated with some limestone close by. So maybe there was a problem there of contamination. I can't really tell, but statistically, one swallow doesn't make a spring. So it's not overly significant. For most samples, it works rather well. Now, looking at the iron isotopes, and this is a plot of only our new data from the paper. And here we have Kiruna again, Grängesberg, Elaco, and we have the layered intrusions again, and the volcanic reference samples. And we also have some of these vein and disseminated samples from Greniusberg, and we have the low temperature hydrothermal samples that plot beyond the magmatic reference field given in orange. Only one single sample, the same sample again. It seems to be anomalous, so there is always one, I can't help it. But here is the literature data that were available, summarized. And what we see is, again, that most of these apatite iron oxide ores, they start out in the orange in the magmatic box, and then they go towards lower temperature values sometimes, or for some systems, we don't even see that this happens. And therefore, there's some good indication that for most of the apatite iron ores, the magmatic box is where things begin. So if we correlate these two kind of systems, then, let's look at it here. So this is all the data we compiled, and the green ones are, again, the low temperature ones. They plot well below the magmatic box and the high temperature hydrothermal box. And if we kind of try to make sense out of this and group them in the lower plot here, then we see that, for example, Elaco goes all the way to the left. So there is some hydrothermal overprint, but it's not necessarily low temperature. I would think of it as medium type temperature. But for most of the other systems, we see a strong origin in the magmatic box. So, and if we take the data out and just look at clouds, this is how it looks. The layered igneous intrusions are firmly in the magmatic box. So are the volcanic reference samples, and several of the iron ore suites. They start off in the magmatic box and move towards hydrothermal processes, mid-temperature hydrothermal processes. And that certainly includes Elaco. So there is an element of hydrothermal overprint. Now, we can test all this, and I don't want to necessarily go into the details here, but if we then want to play with this to check the robustness of these data, we can kind of model this and calculate it as being in equilibrium with magma, or we can test whether it's in equilibrium with hydrothermal fluids at various temperatures. And this is just a very quick calculation examples for a particular samples from Greniusberg. And this particular example yields a magmatic value for the host magma at magmatic temperatures. And if we do that for all the data we have, and we try them for different kind of equilibrium compositions, we find that the red data is when they're in equilibrium with magma, and the yellow data points are equilibrium with high temperature magmatic fluids. And here we get very good indication that there is variations depending on exactly what we assume to be the crystallizing agent, but it changes the overall model very little. It's still all in the magmatic kind of area of this diagram. And for the hydrothermal ones, they are now given in blue. They still fall into the lower part of the diagram, even if we assume all sorts of equilibrium compositions here. So the conclusion from this exercise is that the data are pretty robust, and that this method is actually quite a robust method to employ for distinguishing between magmatic and low temperature hydrothermal processes. So this led us to this little diagram here, where we can broadly summarize that much of the crystallization of the Kiruna ores, the Greniusberg, Elaco, and Bafk, and some other Chilean ones most probably, are starting up in the magmatic range. And these systems will then continue to produce ore deposits when the system cools. All volcanoes have to cool down at some point. They have a lifetime, and therefore there can be recycling of materials. There can be recycling of magnetite, reprecipitation at lower temperatures as well. So that is not strictly a problem, I think. And here's an earlier version of the diagram that didn't make it into the paper. But here, I think most of what we see is actually happening at this area between 8 and 6 and maybe 500 degrees, where the fluid pressure is actually very high. So we may partly crystallize from magma, but we certainly also crystallize from high temperature magmatic fluids. And then, of course, there will be some overprinting in the lower stages of this temperature line. And there we might even have external fluids playing a role, and they would then cause a percentage of the ore to be recycled, reprecipitated, and having a somewhat different isotope signature. So to conclude, overall, the data support primarily a magmatic origin, I believe, for these Kiruna-type ores. And they also record that several of these systems have cooled down while ore was still being produced. And this is what I call the hydrothermal death of these volcanic systems. And a small proportion of the magnetites we sampled, therefore, has different signals. But overall, we must accept that an origin in the magmatic field is what really kind of makes the prime origin most likely. So this is where I'd like to close, and I say thank you for your attention. And of course, you've seen that now. Here's the paper again for those who are interested. I have a few extra slides for our discussion, but I think I'll leave it here, and we can now go and have a little chat about this. So thank you for your attention.